Hello everyone, my name is Vineet and today I'll be presenting our lab on an oscillating spring system. So in this experiment we examined how energy changes in a spring mass system and we focus on energy conservation. So the purpose of this lab was to observe energy transitions in an oscillating spring with a mass released from a vertical angle. We explored key physics principles like conservation of energy, spring force, and energy variations during oscillation. The findings that we saw showed that our model built using GlowScript closely matched with the experimental results with no net change in total energy, supporting the conservation principle. So before we jump in, let's talk about some fundamental physics principles. Here we have the primary equations that kind of guide our experiment. We have the momentum principle defined there. We have the velocity update to calculate the final velocity, the position update to track movement using the equation given, and we have energy calculations where we have the kinetic energy given, the gravitational potential energy, spring potential energy, and total energy. So let's look at our lab procedures. We set up a hanging mass with initial conditions for position, velocity, and time interval. We recorded the x and y position and exported it into a GlowScript to model the system computationally. This pretty much allowed us to track the energy changes precisely. We also have listed the initial conditions, and also the system is the hanging mass and the surroundings is the spring and the gravity. So let's look into it. So when we're looking at our lab procedure, we have our code, which is kind of displayed here, and we use the equations given right here to calculate the spring's position. We also used the equations below here to calculate the kinetic energy, gravitational spring, and total energy. And so what we're doing is for the time timestamp below 9.4 seconds, we're going to be calculating the gravitational force, the spring force on the mass, and also the net force. This is just continued code of what it kind of looks like. So now when we're looking at our data analysis, you can kind of see that we plotted both our tracker X and Y data charts and pasted into a spreadsheet, and then we exported it as a CSV into GlowScript. And so when we're kind of looking at this, there are a couple sources of error that we can definitely account for. But before we dive into that, what we can see is like summing up the changes of individual energy, it always ends up equaling to zero, which kind of, agrees to the conservation of energy law. And a computational model was almost exactly in accordance with our experimental data for X and Y. Some sources of experimental error are that we weren't accounting for drag forces. There's probably some loss of thermal energy, friction, rotational energy, and maybe we didn't correctly mark the center of mass when we're tracking frames. So what does this all mean? The energy principle was confirmed. The total energy remained constant over time as the graph shows. Changes in individual energies canceled out, showing no net loss or gain, which is consistent with the conservation of energy. Now, what if the oscillation period estimate? So we kind of estimated the oscillation period by analyzing data from both the x and y positions. The y-axis estimate gave us a period of around 1.52 seconds, and while the x-axis estimate was around 1.625 seconds, and there's a small variation of 0.101 seconds, and this variation is probably from factors like camera distortion, inaccuracies in center of mass tracking, and drag forces. So ultimately, our lab demonstrated that the conservation of energy principle holds true in a spring mass system despite small minor changes in errors. Our computational model aligned closely with our experimental data, showing the power of modeling in physics. So I thank you for watching through my lab, and let me know if you have any questions in the comment section.